A warm welcome to you from Shaw Academy. Your journey of becoming a cybersecurity certified user continues here. In the first 3 lessons of the cybersecurity course, we learned how to set up a small business to our ISP. We have viewed some of the capabilities of wireless adapters, as well as the different deployments in business network. In this lesson, we will be delving a bit deeper into our network. You might recall that in Lesson 3, we discussed how routers are able to transmit traffic from a LAN to a WAN. In this lesson, we are going to have a closer look at addressing in network devices. A really big welcome from all of us here at Shaw Academy. We are here to help you learn the skills you need to succeed today. Edwin is the subject matter expert for this course. He has a wealth of knowledge and experience and is passionate about sharing it with you. In case you forgot, I am Nina Smith, the presenter of this course. In this lesson, we'll be looking at the physical and logical addressing in network devices, such as your laptop. In this lesson, we're going to help you to understand the difference between private and public IP addresses, explore network address translation, NAT, and how private addresses are converted to public IP addresses with the NAT, explore IP addresses, and explore MAC addresses. We'll look at the differences and how routing works with each one. When a program is initialized in a system, an IP address is generated by the CPU, Central Processing Unit. In this section, we will be looking at private and public IP addresses. But let's start at the very beginning. What is an IP address? The addresses generated by the CPU when a program is initialized in a system are referred to as logical addresses. They are not physical, but are created for management purposes. That's why they're also often referred to as virtual addresses. These logical addresses are linked to physical addresses by hardware embedded on the motherboard, which is also known as the Memory Management Unit. Now, in this section, we will cover several important aspects of logical addressing in a network. For starters, let's discuss the difference between private and public IP addresses. A private IP address can be viewed as the use of a private IP address space in a network, where the IP contains a unique number or numerical representation that identifies specific devices on the network. The IP address is usually assigned to a specific interface on the network device. There are certain specifications that are defined in the private IP address ranges and often used in LANs. These are known as the IPv4 and the IPv6. We'll talk more about these in a while when we get into exploring IP addressing a bit further. A public IP address is a unique identity that is used to communicate outside the LAN. This address space is managed globally by the Internet Assigned Numbers Authority, the IANA, and the Regional Internet Registries, RIR, responsible for different regions. Now, the Regional Internet Registry consists of 5 regions, one for the Asia-Pacific region, another for Canada, USA, and some Caribbean islands. The third region covers Europe, the Middle East, and Central Asia. LACNIC is responsible for Latin America and some Caribbean islands. And AFRINIC handles the African region. When discussing IP configuration and IP addressing, there is common terminology that is used. We thought it would be useful to look at some of these terms. A static IP address. Now, static often means constant. This means the IP address never changes. It stays fixed to the end device, except if configured otherwise. An example would be the public IP that have been assigned to a WAN by the ISP. Then a dynamic IP address. Now, the IP address is bound to change from time to time, particularly when an IP address has been issued by a DHCP server with a lease time. When this expires, a new IP address will be issued to the end devices. Next, a shared IP address. Now, this is like a pool of connected devices in a network where they all use one IP address for their connection. A good example will be hosting of web pages on a server. Website owners are able to host their site on a shared IP without ever being affected by another site hosted on the same server. And then a dedicated IP address. Now, this is when only one user is able to use the IP and it cannot be shared. A good example will be large websites or e-commerce sites that often use a dedicated IP address to have full control over the IP. A port number is a number that is assigned to different processes run over the internet. It is used to identify different protocol traffic on a network. A good example will be port number 80 for HTTP, Hypertext Transfer Protocol, 23 for Telnet, and 25 for SMTP, Simple Mail Transfer Protocol. Now you get all classes of IP addresses that are used to identify the range of IP addresses that can be assigned to an end device. For interest, here is the range of classes of IP addresses. You will find this list included in the summary notes for this lesson. A class is 0 to 127 with default mask 255.0.0.0. B class is 128 to 191 with default mask of 255.255.0.0. C class is 192 to 223 with default mask of 255.255.255.0. And D class is 224 to 247, not currently used. And E class is 248 to 255, also not currently used. You will also find this table in the summary notes for this lesson, or you could snap a screenshot of it and save it to look at it more closely later. We started this lesson by explaining that the virtual addresses generated by the CPU when a program is initialized in a system are referred to as logical. A logical address is vital for computing and networking. Without logical addresses, computing would be impossible. Now let's explore the functions of a logical address a bit further to understand why we say this. There are many functions of logical addresses, but right now, we're going to look at the two major functions of a logical address. That is, address mapping and translation. Address mapping, also known as the mapping function, is the process that makes the addressing easily accessible by the system. The ability to access an address and to have it retain its identity over the course of the access is unique to this access method, and it facilitates good communication in a network. It also helps to increase efficiency and reduce complexity. Address translator refers to the manipulation of IP addresses to identify devices over the internet. It helps to map private IP addresses within networks to public addresses that are routable over the internet. This system is often referred to as Network Address Translator, NAT. Something worth looking at a bit closer, which we will do next. Then, of course, we still have lovely old Morpheus, or maybe not so lovely for you. Please do let us know if that's the case. Remember to rate the responses that you receive so that we can improve them. If you have any technical issues or a problem with anything, any reply that you've received via Morpheus, please email us on support@shawacademy.com. Exploring network address translation is basically how a private address converts to a public address when connected from a LAN to a WAN. To explain it in a bit more detail, network address translation is a logical process that maps multiple local private addresses to a public IP address and vice versa before transferring the data from the local hosts. There are three different types of NAT used for different reasons. These are static NAT. Similar to static IP addresses mentioned earlier, every time connectivity is needed outside the LAN, the NAT is configured to use the same public IP address. Now, this IP address is manually configured to the router. Then we have dynamic NAT. The public IP address changes every time a connection from the LAN to the WAN occurs. These are usually practiced in a big organization where security is vital. And then we have port address translation, PAT. This is a form of dynamic NAT, but a port number is associated with the IP address for identification reasons. So you probably already know, or should do by now, that every connected device on the internet has a unique identifier, which is an IP address. Think of these as each of us having our own PO box address so that we can receive mail. Now think of all the connected devices sending different data across huge geographical areas. This is done using the TCP/IP protocol stack, which is the Internet Protocol suite that enables end devices to communicate across different networks. We mentioned that there are certain standards for IP addresses when we're looking at private IP addresses. There are two types of IP addresses that are used to identify machines connected to a network. They are IP version 4, IPv4, and IP version 6, IPv6. The IPv4 standard is made up of 32 binary bits to create a single unique address on the network. It is represented by 4 integers. In computing, integers are data types, separated by dots. Look at this example. The IPv6 was created to provide more unique IP addressing within the original TCP/IP protocol over the internet. Now, this standard is made up of 128 binary bits to create a single unique address. It is represented by 8 groups of hexadecimal numbers separated by colons, like this. Note that the groups of numbers with zeros use a colon separator to save space and mark the gap. A quick did you know stop to explain Internet Protocol version 6 as the replacement for IPv4. Basically, IPv4, which is the original address scheme, is running out of addresses. So, due to the exhaustion of IPv4, as well as our ever-expansion of the Internet of Things, IP version 6 will allow many more devices to seamlessly connect to the Internet. Let's now look at how to create a logical division of an IP address. This is commonly referred to as subnet, and it's basically a network inside a network. A subnet can practically divide any network into 2 or more parts. Subnets clearly make networks more efficient. Now, through subnetting, network traffic can travel shorter distances without passing through unnecessary routers to reach their destination. To create a subnet, you change the IPv4 address from binary notation to decimal notation. Let's look at some applications of a subnet of an IP address in a network. Look at this example. Now, from the subnet mask, we can see that it has 3 octets, which has 24 bits. From this IP address, we see the first 3 octets, 192.168.1, refer to the network address. The last octets, 0, refer to the host address. The network address identifies the particular network the IP address is on, while the host address identifies the number of host or connected devices on that particular network. In this specific example, any IP address with the IP 192.168.1.0 would fall under the same network. From this example of a subnet mask in the IPv4 standard, we can see that a subnet mask consists of a series of bits. Every bit is mapped to the IP address. And in the IPv4 standard, the most commonly used subnet masks have complete octets of ones and zeros. If you would like to read more about subnetting, you can check the bonus content for this lesson in your toolkit. Okay, let's now look at how IP addressing is used for communication over the internet. There are 4 methods of addressing that we will look at now. They are Unicast Addressing, Broadcast Addressing, Multicast Addressing, and Anycast Addressing. Unicast addressing is the process of a single host sending data to a single destination. IPv6 includes 2 different unicast addresses. A global unicast address that is globally unique on the internet. Have a look at the example on the right. And the other unicast address for IPv6 is a link local address. This is used only on a local network link and is not valid nor recognized outside the enterprise. For example, before we move on to the next type of addressing, we thought it would be a good idea to stop and quickly look at an example of unicast addressing called ARP, Address Resolution Protocol, ARP. You will notice that ARP actually also uses broadcast addressing. Right now, we're just going to talk broadly about ARP. We do explore it in more detail in the last lesson of this module. Now, we have mentioned ARP before. It's an address resolution protocol used to discover the link layer addresses. It maps IP addresses to hardware addresses, which is the MAC address. ARP is a good example of a unicast request, and during the course of Lesson 8, we will analyze some ARP requests sent by network devices. Now, because these MAC addresses are unique to the physical component of the devices, the ARP request will be able to identify these devices on the network. Okay, let's explore how ARP messages work. There is an ARP request, which is a broadcast message containing the source IP address, destination IP address, and request for the MAC address of the destination, and an ARP reply. The unicast contains a reply from the destination IP address and MAC address that is sent to the initial sender. From the diagram, we can see the ARP message must contain the relevant information to be able to establish connectivity. Now, for us to be able to establish connectivity, both connected devices have to communicate with each other. When we look at the ARP message in Lesson 8, we will use the Internet Control Message Protocol ping echo request to generate traffic between 2 connections so that we can explore the ARP request in more depth. So what is the Icmp, Internet Control Message Protocol? As we've just mentioned, the Icmp is a protocol that is used by the ping utility to verify connectivity between 2 devices. The Icmp ping echo request contains the following messages from echo: response, request, such as destination unreachable, when the machine or laptop is not on a network. Icmp provides feedback for diagnostic or to report logical errors between connected devices. Broadcast addressing enables transmission to every connected device in a LAN using switches. The address is the highest numeric value of the IP address. For example, the broadcast address of a Class C 192.168.1.0 network is 192.168.1.255. Multicast addressing is used to deliver a package to a group of destinations. Any packet sent to a multicast address will be delivered to every host connected on that network. A good example of multicast addressing is emailing in big companies where there are a lot of employees within the company's domain. One employee in the company can easily send a message to every employee within the company by adding every address to the company email list. Another good example of multicast addressing is conference calls where one user can communicate with multiple users simultaneously over the internet using applications like Zoom and Skype. Anycast addressing is similar to multicast addressing, but in this case, packets will be delivered to only one random host in the whole network. These addresses don't have a specific range, as they are exactly the same as regular unicast addresses. This means that a host has no way of distinguishing a unicast from an anycast address when it sends a packet. A good example of anycast will be the use of DNS queries. You may recall that DNS stands for Domain Name System, and it helps translate IP addresses into domain names, which are more readable and easier to understand. When a network device searches for a web page hosted on a web server, that device is connecting to a particular web server. If you think about it for a second, there are billions of different web servers on the internet and more being created every day. So DNS is configured on a connected device to help choose a routing path out to the internet, which is basically Anycast addressing. So we've looked at IP addressing. We noticed that the terms IP address and MAC address are often misused. So we thought we'd include a section that explores MAC addressing. That's Media Access Control for short, to make the difference between the two more clear. A MAC, Media Access Control address, is an identifier for a particular network interface in an end device. MAC addresses are usually configured and tied to the physical interface on the end device by the manufacturer of the device. Do you remember this from when we looked at wireless adapters in the previous lesson? We can clearly see from the circles that the top and bottom interfaces, not the loopback interface, refer to the MAC address in the device. The interfaces present in this particular device are an Ethernet interface for wired connection with a MAC address, a loopback interface with no MAC address because it is virtual, and a wireless interface used for wirelessly connecting with a MAC address. Did you know a loopback interface is a virtual interface that is always reachable and mostly used for debugging tasks? This is because its IP address can always be pinged if any other switch interface is up. So there were MAC addresses in two of the interfaces on the example we have just looked at. Let's unpack a MAC address by looking at this example. A MAC address often comes as a string of 12 digits separated by semicolons. The digits range between 0 to 9 and A to F. Since MAC addresses are unique identifiers, every MAC address is unique. The first 6 digits of a MAC address represent the adapter's manufacturer, and the last 6 digits represent the identification number for that model of adapter. Now, there are several uses of MAC addresses. Two very important uses are that they aid connectivity. Do you recall us learning that switches are network devices with the ability to transmit data within the same subnet? This is done by using MAC addresses. In the OSI model, the data link layer comprises of 2 sublayers, which are MAC, Media Access Control, and the LLC, Logical Link Control. MAC addresses provide a means for exchanging data frames using switches. For security, because of their uniqueness, they can be used for MAC address filtering and blocking traffic that comes from machines or devices. We will go into this in more detail when we get to the section on using MAC addresses to secure network devices in Module 2. To make sure we're all clear about the differences between MAC and IP addresses, let's look at a quick summary of each one. A MAC address is a physical identifier on networking devices. It operates in the layer 2 of the OSI model, data link layer. It often comes as a string of 12 digits separated by semicolons, and the digits range between 0 to 9 and A to F. It is managed by the manufacturer of the device. The manufacturer burns in the address in the device hardware component to identify the device on a network. And finally, it is often pre-configured in a device if the device has a network card interface installed. Examples of such devices include routers, switches, network repeaters, Wi-Fi extenders, and network printers. Whereas an IP address is a logical address of connected end devices in a network. It often comes as a 32-bit numeric address for IPv4 and 128-bit numeric address for IPv6. It is managed and changeable by the ISP. It is used to identify the device in a network, and it is not pre-configured in an end device if the device has a network card interface installed. We are going to wind up this lesson by looking at how IP addresses and MAC addresses affect routing, starting from a sender's end device, laptop A, to receiver's laptop B. But before we go into how IP and MAC addresses affect routing, let's quickly stop to make sure we all understand the term routing. Routing in computing is a process of selecting a path for traffic in a network, or between or across multiple networks. So let's take it step by step to see how IP and MAC addresses affect routing. Laptop A connects to a network through the use of a network interface card, either through the wired or wireless interface. If a DHCP server has been configured on the network, the DHCP server will assign an IP address to laptop A so that it can talk to laptop B. A data frame is created from laptop A. That's a packet containing the source IP, destination IP, and other information. When the packet reaches the switches, the switch checks to see if the final destination of the packet is to any device on its own LAN. The switches do this using a MAC address table. If the intended destination is on the same LAN, the packet is sent directly to laptop B. If the intended destination is on a different network, the packet is sent to the router. The router inspects the packet to get the relevant information and sends it out to the internet through the ISP. In this lesson, we looked at the differences between private and public IP addresses. We also looked at network address translation, how private addresses are converted to public IP addresses. We then jumped into common functions of logical addresses. We spent quite a bit of time exploring IP addresses, and our last section of the lesson focused on MAC addresses and the difference between MAC and IP addresses, and routing using the two addresses. In the next lesson, we will be looking at the concept of the intranet and how it works, and we'll explore file sharing on a network. So it's over to you to practice what you've learned in this lesson. Your task is to compare your private IP address with your public IP address. We have given you step-by-step instructions to follow depending on whether you're working on Windows, Mac, or Linux. So the first step is to find your private IP address. And then you'll use these steps to find your public IP address. Please note that this challenge is to give you a chance to practically experience the theory you learned in this lesson. You should never share your IP with anyone. You have your weekly assignment coming up. Remember, it is not compulsory and does not count towards your final mark, but it does help you prepare. There are summary notes available for purchase within your profile on our website and app. These are a fantastic resource helping you to prepare for the assignments and answering any questions you have around the content. How are you finding the course so far? Are we living up to our mission? Are you finding the course flexible and engaging? Are you learning your own way? And have you mastered any practical skills? Give Morpheus your feedback or email us on support@shawacademy.com. Well done on completing Lesson 4. You're halfway through Module 1 already. See you soon for Lesson 5.